All right, next lesson. Next lesson. Last lesson we talked about how light exhibited properties of wave, right? So we there was an experiment to prove that light was exhibited properties of wave using the double slit experiment, right? You saw the diffraction pattern. Yeah. And so in this lesson, we're going to talk about evidence that shows that light also behaves as a particle. And so if you, as a reminder, as a refresher, waves are just a disturbance of energy that oscillate around an equilibrium point, right? It's just energy. Waves are just energy. And a particle can be defined as something of a defined energy, right? There's a defined energy. It has physical or chemical properties and has specific energies, right? They don't really change at all. They're specific defined energies. Before we go into that, let's talk about atoms. Let's go into a brief history of atoms. Rutherford's model, which is wrong, right? Nucleus is in the middle, and then electrons surround it, and they move in circles, which is wrong. There are problems with the Rutherford model, if you want to figure it out later. Now we come into Bohr's model. And Bohr's model is a more recent model, even though that there are still problems with the Bohr model. Most of you learn this in chemistry class, and you will learn about this right now in physics class because it is fairly accurate up to a point. Right? It's fairly accurate for a hydrogen atom, but is not the ultimate model, right? It's not the all everything is correct model. But it's good enough for the high school level. So again, the Bohr model, electrons exist in certain energy levels, right? So the nucleus is, which is this red dot, is in the middle, and the nucleus is in the middle, and then there are energy levels surrounding it where the electrons exist, right? Electrons exist in these energy levels being n is equal to 1, n is equal to 2, n is equal to 3. So first electron energy level, second, and third. All right, again, this is the Bohr model. Again, it's not entirely correct, but it's good enough. Now, I want you to watch these two videos, right? So the first video is 2 minutes long, and the second video is 9 minutes long. They are really good videos though, by again from the same TV show called The Cosmos, hosted by Neil deGrasse Tyson. So please do watch both of these videos. So in Tyson's video, he explained that if light entered an atom, right? If light hit an atom, what would happen is that the electron would go from one electron level to another electron level, right? As you can see in the first GIF right here. So if you shine a frequency of red light onto this electron, well, what's going to happen is the electron is going to gain energy and it's going to go up an electron level. But what happens after that is after the electron gains that energy, at some other point in time, it will spontaneously emit energy as well. And the energy that the electron emits is very specific. It emits that same exact frequency of light, that same red light. So red light is coming in with a certain frequency. And when this electron goes back down to this original energy level, it emits that same red light, that same frequency of light. Same thing is happening in the third GIF, right? This is light of a higher energy now. It's probably in the closer to the ultraviolet range. And it has more energy. And so because it has more energy, the electron is going from the ground level, and I'm assuming that this is the ground level. I don't know if it is, but regardless, it goes from the bottom level up 2 levels. So you can clearly see that as you gain more electron levels, the more energy you're gonna have, and so, and therefore that the light that is coming in, whatever frequency of light this is in, it has a higher frequency of light. It's a higher frequency, meaning that this light has more energy. And, and it's increasing the amount of energy levels this electron is going up. And you see the same thing happening again as it falls down from the excited state back down to the ground state. In the excited state, the electron emits that same frequency of light, emits that same ultraviolet light, and it goes back down to the original energy level. But there's something happening here that you're not seeing in the second GIF. Something's not happening in the second GIF, right? Even though you're shining light onto this electron, this electron is not going anywhere, right? It's not going to other electron levels. It's not moving. Well, why is that, right? Clearly, any frequency of light has energy. And so the thinking would be that, well, if you shine any type of light, it should move up electron level. And that's something that wasn't discussed in Tyson's video, because that gets into a more difficult concept that we're going to be talking about today. So why does that not happen? And let's talk more about Bohr's atom, right? So the electrons exist in certain energy levels, right? There are multiple energy levels. And we call it N1, N2, N3. Obviously, these are energy levels. All right. On this right-hand side, you're gonna see a diagram, right? And so there's hydrogen up here, and what this diagram is saying, it's showing the energy levels for a hydrogen atom. And it's showing the energy levels for a hydrogen atom. And these numbers right here, n is equal to 1, 2, 3, 4, 5, 6, and infinity and beyond, they're telling you the ground state, or rather the energy levels, right? Different energy levels. So there's first, second, third, fourth, fifth, and sixth. Now, and I want you to take a look at the numbers on the side. The numbers don't really matter, right? We'll talk about why the numbers start from a high number and go back up to a low number. Even though we just said in the video we know that the higher energy level you are, the more energy you're gonna have. So we'll talk about why these numbers are instead going from a high number down to a lower number later. But for now, just bear with me. All right, for now, just bear with me. And so we're gonna explain why different frequencies of light, right, like yellow or green, don't really make an electron go up in an energy level. And while some other colors of light, some other frequencies of light do. Well, let's take a look at this. And we're going to define light as a photon, right? So photons make up light. Right? Photons make up light. So here you see n is equal to 1, right? The ground state. And n is equal to the second electron level. And so for this electron at the ground state to go to the second energy level, well, if you look at everything over here, you'll see that, well, all of these energies are 10.1, 10.7, 10.6, 10.5, and the only different colored one is 10.2, right? It's instead of purple or magenta or pink or whatever color it is, this is in red. And so there must signify something. Well, if you take a look at this, negative 13.6, negative 3.4, 13.6 minus 3.4 is 10.2. There's that number again, right? 10.2. The difference in number between the second ground state and the first ground state is 10.2. And if you take a look at this, well, a photon with an energy of 10.2 electron volts, which is what this EV means, is going to make this electron go up an electron level. Whereas any other frequency of light with different energies, is going to go straight past this electron and not cause it to move up, which is what's being reflected in this second GIF. There must be, for you to go up in an energy level, an exact energy, an exact frequency of light must hit this electron. Any other energy, any other frequency of light is not going to excite this electron. It's not going to make this electron go up in an energy level. The same thing is true for n is equal to 2 to n is equal to 3. For an electron to go from the second energy level to the third energy level, the photon, the frequency of light that's coming in and hitting that electron, must have an exact energy of 3.4 minus 1.5, which is 1.9. So to go from the second energy level to the third energy level, the photon must have an energy difference between these two levels, which is 1.9, right? It must have exactly an energy level of 1.9 electron volts, the exact frequency of that much. There is a way to convert the frequency of the light into an energy. There is. We don't talk about it though. It's called a Planck-Einstein relation. We don't really care about it. Well, I'm not going to cover it this week, but you can. So that gets in the first step of talking about how light is a particle, right? Because if light is a particle, it must have a defined energy. Particles have defined energies. You cannot change it. They have set and defined positions and energies, whereas waves do not. So there's one evidence that light is a particle, or shows properties of a particle. And so let me talk about a bit more. So if you want to go from the first ground state all the way to the third electron level, well, you do 13.6, which is at the ground state, minus 1.5. And so the amount of energy to go from the first ground level to the third ground level, the third electron level, I keep saying ground for some reason, is 13.6 minus 1.5, which is going to give you 12.5. Not 12.5, 12.1. So for you to go from the first energy level to the third, you're going to need 12.1 electron volts. You're going to need an exact light frequency with an energy of 12.1 electron volts to go from the first to the third, which is really what's happening here, right, in the third GIF. It's going up 2 energy levels instead of 1 in the third, in the first GIF. And then when the electron drops back down, it's going to emit that same frequency of light. It's going to emit that same frequency of light. So this is also what Tyson talked about in the video. They're called spectrums, right? Because in a star emits light, and you can tell what elements a star is made up of if you look at it with a spectroscope. I was going to do this in class, but unfortunately we don't have class. We actually do have spectroscopes. If you ever took in earth science at the school, maybe you've used them before. So if you ever take a look at a sun, you're going to see an entire spectrum of light with a few caveats. You're going to see dark bands through those in that spectrum as well. This is because, and it builds on this entire concept, that elements can only absorb certain energies of light, certain frequencies of light. Any frequencies of light that elements don't absorb goes right past the atom, right? So if you take a look at this atom, whatever this is, I don't even know. I actually Googled this image. you see that different frequencies of light are going through these elements. It's going past these elements, and you see something. But the frequencies of light that the elements do absorb, you're not going to see, right? So take for example this green light. It's getting absorbed by this element. And when you try to look at through a spectroscope on this end, well, the only color that's missing is going to be green light and yellow light, whatever this is, yeah. So you're going to be missing a few bands of color. And that's called the absorption spectrum. Right? If you want to read more about it, here it is. You're not going to be asked questions about it. And the light that does get absorbed by the element, that element is going to re-emit that light because the electron from a higher energy level is going to go back down to the ground state and it's going to emit that light somewhere else. And we call that the emission spectrum. Right? The emission spectrum are the frequencies of light that an element absorbs that get re-emitted. When that light gets re-emitted, due to electrons going back down electron levels, this creates an emission spectrum, right? Like this. So this is the emission spectrum of hydrogen. If you take a look at the top right, the bottom is a spectroscope. Top one is an absorption spectrum. Cool. You're not actually going to be questioned on this. So again, if you take a look at this, well, how do we know? Well, if a hydrogen atom, if an electron from the 6th ground state drops back down to the second, I keep saying ground state, from the 6th electron level to the 2nd electron level, well, it's going to emit this frequency of light. If the electron drops from the 5th electron level to the 2nd electron level, it's going to emit this frequency of light, and so on and so forth. This is how you get light. This is how we know what elements different stars are made up of, right? That's why we can say for a close certainty what they are made up of, because we know the spectrums of each of these elements. This is what your questions are going to be on. All right, so on the third page of your reference table, you can see this diagram. You're going to see the electron level diagrams of hydrogen and mercury. And there's one vocabulary word I want to discuss, which is called ionization. Ionization is when electrons are free. That when you've given enough energy, when you shined enough, when you give enough energy to this electron to get it out of the atom, right? To expunge this electron out of the atom, to ionize it. So when electrons gain enough energy to leave the atom, they become ionized, right? Which is this point. So to ionize a hydrogen atom, to get an electron all the way from the ground state and out of the atom, well, you're going to need to shine a frequency of light that has enough energy of above 13.6. So you need a photon of light that has at least 13.6 electron volts to get it out of hydrogen. Also, this is also how neon lights work, right? So this is also how neon lights work. You give enough energy to go up a few electron levels, and then when the electrons drop back down, you get light. You get certain colors of light. And this right hand side is for mercury. So to get electron out of all the way from the ground state, you need a light with a frequency and energy higher than 10.38 electron volts. But let's say you shine a frequency of light that has an energy of 15 electron volts onto hydrogen. right? 15.5 electron volts to be exact. Well, how does that work? Where does all that remaining energy go? You know that 13.6 electron volts must be devoted to ionizing that electron. But where does the remaining energy go towards? Where does it go? Well, if you take a look at this right here, this formula right here, the energy of the photon that's coming in is going to equal to the kinetic energy of the electron plus the energy of ionization. And the energy of ionization for a hydrogen atom is 13.6. So for example, if your photon has an energy of 15.5 electron volts and it hits a hydrogen atom, the energy and the energy of the ionization of a hydrogen atom is 13.6 electron volts. Well, the remaining energy goes into the kinetic energy of the emitted electron, right? So this electron now that you've just forced out of this atom has a kinetic energy of 1.9 electron volts. And then you can convert that into joules using your reference table, right? Again, you can figure out how much energy a photon has by doing Planck's constant times the frequency of the light. Planck's constant is also on your reference table. Again, we're not going to talk about this week. It's going to be an optional lessons. Now, what you've all been waiting for. Questions. So an electron in an excited mercury atom is in energy level G. Alright, so if you go to your reference table, go to the third page, at G, it says negative 2.48 for mercury, right? That's your electron volts. And they want to know, well, what is the minimum energy required to ionize this atom, right? To get it above a level J, which is 0.00. Well, there's an easy way to solve this problem. What is the minimum energy to get this electron out of this atom? Well, if the energy at level G is negative 2.48, you just need at least plus 2.48 electron volts, right? You need at least this much energy to ionize mercury if an electron is at level G. So let's see. It's actually that simple. There are really no tricks involved. Number 2, a photon is emitted as the electron in a hydrogen atom drops from n is equal to 5 directly to n is equal to 3. Right, so you're looking at the hydrogen atom now, and it's going from n is equal to 5, the 5th energy level, to the 3rd energy level. What is the energy of the emitted photon? So again, if you drop down an energy level, if you drop down energy levels, go from n is equal to 5, and then n is equal to 5, you have, it says negative 0.54. And at n is equal to 3, you have negative 1.51. So what's going to happen? Well, you just take the difference of these numbers, right? So if you drop from 0.54 to negative 1.5, negative 0.54 minus negative 1.51, and you should get a certain number, and that's going to be your energy of your photon, right? The answer is you just solve this math. So that's number 2. Number 3, electron in the C level of mercury atom returns to the ground state. So in mercury at C, you have negative 5.5, and it goes down to the ground state, it's 10.38. And again, these are electron volts, and this is a 5. This is a 5. Which photon energy which photon energy could not be emitted by the atom during this process. Well, here's the thing. What the electron can do, it can go from C. Here, let me just... There are a few routes that this electron can take, right? It doesn't have to go directly from C to A. It doesn't have to drop directly from C to A. It can go from C to B, right? From electron level C to B. And it can then go, after it goes from C to B, it can then go from B to A. Or it can go directly from C to A. So there are three possible choices here. Three valid energies that can be emitted. Three photons that can be emitted here of different energies. So what you're going to do in this problem is, well, figure out, well, C is negative 5.52. B is negative 5.74. Let me actually just erase this. Give myself more room. Yeah, let's erase all this. So again, let me rewrite it. A is negative 10.38 electron volts. So if you're going from C to B, you're going from negative 5.52 minus negative 5.74. This is also the reason why they're all negative, by the way. And then you're going to get 0.22, I think. Yeah, electron volts. So this is the energy. This is one possible photon energy that can be emitted. This is one possible photon energy. That's from C to B. So that's for this choice. So choice A is correct, right? So you're looking for a different choice. It's either B, C, or D. And figure out the energy level for this. Figure out the energy differences for these. And then find the one that doesn't fit. And that's your answer for number 3. An electron in a mercury atom drops from energy level F to C. So F to C. F, your electron energy level is negative 2.68 electron volts. And C, it's negative 5.52. And it's asking you, what is the energy of this photon that is emitted when it goes from F to C? Again, you do the same exact thing. Just subtract them. Literally just subtract them. Alright, and then you get a certain number. 5. Same thing. Same exact process. I believe in you guys. Now, even though you've done all your questions now, it's pretty much done. You can't really explain why light is a particle. Well, why light exhibits properties of a particle without explaining what the photoelectric effect is. So, based on Young's double slit experiment, there was evidence that light was a wave, right? We saw the diffraction pattern. So definitely light exhibited properties of a wave. And so based on this evidence, physicists predicted that increasing the amplitude of light waves would increase the kinetic energy of the emitted electrons. Think of constructive interference. If you increase the amplitude, if you keep stacking light, you're raising that amplitude and you're increasing energy. And if you go back to a previous slide, right, if you increase the energy of the photon, let's look at this formula right here. If you increase the energy of this photon and the energy of ionization stays the same, right, the energy required to emit this electron stays the same, well then the kinetic energy of the electron is going to increase if the energy of the photon increases. So that's what they predicted. That's what this formula predicts. And that would provide also further evidence that light was a wave. But that didn't happen. In their experiment, increasing the amplitude of light, adding more light waves, did not increase the kinetic energy of the electrons emitted. So no matter the intensity of light they shined on these electrons, the kinetic energy of these electrons were constant. They did not change no matter the intensity of light, right? You could add 1,000 photons or 50 photons onto these electrons. Didn't matter how many photons you shone on these lights. The kinetic energy of the electrons were all the same. It's just that if you shone 50 photons onto these electrons, less electrons would be emitted at a slower rate. But their kinetic energies were the same. If light was truly and only a wave, if it truly and only was a wave, then all these photons could stack on top of each other. And then what would happen is that the kinetic energy would increase if you stacked all of these photons on top of each other, right? Due to constructive interference. But that's not what they saw. Um, and the only thing that could change the kinetic energy of these photons was if they used different frequencies of light. Frequencies of light that had higher energy. So, and this really is huge evidence that light it also exhibited properties of a particle. Because if you think about particles have defined energies. They cannot be stacked on top of each other. And each frequency of light has its own energy associated with it. So the only way to increase the energy of the photon is if you change the frequency of light. If light was a wave, you could also change the energy of the photon by adding more waves, adding more photons. But is not the case. Each photon of light has a specific energy. For example, you need at least an energy of 13.6 electron volts to emit to emit an electron from a hydrogen atom from the ground state. But you need at least one photon of that energy. You cannot have 3 different photons with 5 electron volts each. Those 3 photons cannot come together and then help each other to emit this electron. That cannot happen. They're not gonna there's no teamwork involved. It has to be one photon with at least that much energy to emit this electron. These photons do not stack. They do not constructively interfere. Or in this case, they don't constructively interfere. So, but you do see them constructively interfering if you shine them through double slits, right? Obviously. And so this was further evidence that light exhibited properties of a particle. So, in the end, in conclusion, light can be a wave and also can be a particle. It exhibits properties of both, which we call wave particle duality. Great. So what I'm about to show right now is a PhET simulation of the photoelectric effect. So here we have sodium, right? So you have a sodium right here, and the light bulb is right here. And let's say I increase the intensity to 10%, right? And so the wavelength of the light that I'm shining on sodium right now is 469 nanometers. Let's actually move that a bit. I didn't want that there. 472 nanometers. All right. And so you see these things are popping from the sodium are electrons. And so the electrons are going from here all the way through the other side. Now, increasing the intensity of, and these are photons, increasing the intensity of the photons, right? Increasing the number of photons hitting the sodium doesn't increase the kinetic energy of these electrons. The only thing that's happening is that there are more electrons being released. They're not going any faster or slower, but they're more or less the number of electrons being emitted increases. If you're wondering why there are two speeds here, it's because maybe one electron is going from the ground level and then getting emitted. As a result, has less overall energy that can be devoted to kinetic energy. Whereas if the electron is emitted from the second level, there's more energy devoted to kinetic energy. So that's why it has more speed. So the only thing that really changes the kinetic energy of these electrons are if you increase the frequency or decrease the wavelength of the photons, right? So now the photons are flying much, much faster, and their kinetic energies increase. So it doesn't matter if you change the intensity, the kinetic energies are still the same. It's just that there are less electrons. If you increase the intensity, there are more electrons, the kinetic energies are the same. So the only thing that changes is the frequency of the light, or rather the wavelength. Right, so now I'm just like a bunch of colors shining on. And so that really reinforces, that really shows you the photoelectric effect. And again, different materials are gonna have different wavelengths and frequencies that can emit their electrons. Right, so take for example zinc. We switched to zinc, and even though we kept the same frequency or wavelength, nothing's happening. What we're gonna do, let's actually, maybe it's all the way on the other side. No, it's all the way over here. Yeah, so it takes a much higher frequency or lower wavelength for electrons to be emitted. It doesn't matter how I change the intensity, the kinetic energies of the electrons stay the same, it's just that there are less of them overall.